How's everyone doing today? First sort of demo session of the morning, I guess. At least the room was empty when I walked in here to set up. So what I'm going to talk about today is how we deal with running blockchains in our cloud environments. So before I get there, a little bit about me and my company and why I'm standing up here. So my name is Kuhlman. I'm the CEO of Monax. We're a Hyperledger member. We've been in this game and doing this, playing this game of clouds and blockchains for a wee while now. We're a 4-year-old company. We were the first to market with a permissionable blockchain before anybody knew that that was actually going to be a thing. I'm talking some of that history tomorrow afternoon if people are interested. We were also the first to market with scalable packages of smart contracts that could be mixed and matched and deployed to a range of different use cases over time, predominantly Solidity-based smart contracts. We're the primary maintainers of Hyperledger Borough. And so what I'm going to show for the rest of this will be a little bit Borough focused, but in general it will be, I'll try to abstract it as much as I can across different DLT frameworks that exist. Currently what our company does is we're working on two things. We're working on a public permissioned blockchain network called the Agreements Network, which is focused on being a contract lifecycle management tool for managing legal contracts. And the core piece of the Agreements Network are, well, there's two core pieces from the blockchain perspective to the Agreements Network, one of which is Hyperledger Borough, which the entire system is built upon, and the other is a business process execution engine written completely in Solidity. Currently, we call that project Blackstone. It's, I think, probably, well, it probably is the largest amount of Solidity code that has been open sourced. We will be looking to move that into, we will be submitting it for incubation early next year into the Hyperledger project because there are a whole range of blockchain use cases that leverage business process modeling as a core piece of their use case. On top of that, we have a SaaS-based application that's focused on small businesses. And so what I'm going to talk about today is how we boot blockchain networks, how we manage blockchain networks in the cloud, how we deal with log management, and how we deal with monitoring. So this is a very DevOps-focused talk, and I'll be primarily focusing on a few tools that lie underneath what we do. In general, we use Terraform, Helm, and Kubernetes as our operational runtime, and obviously with Docker images along the way. So I'm going to be talking about predominantly how we piece those things together into a coherent operational environment. I like conversation talks, so you can see there's no slides. This is a demo talk. I didn't prepare any slides because I'm predominantly going to be demoing. Feel free to stop me at any time and ask any questions. We have a mic up here somewhere, which you can use, or if you just want to ask an offhanded question, let me know and I'll repeat it. If I repeat it, it's just for the recording. So to get started, I'm going to trigger a deployment of an entire platform with one click. And what you'll start to see here as our CI system boots up is that first we're going to run through an initiation sequence that is going to set up Terraform in our CI system, and then we're going to go through an initiation of building a specific blockchain network. So how do we do that? It's relatively simple to boot an operational runtime in a Kubernetes environment. However, managing those things over time, if it's a blockchain system, can get a little bit tricky. You have to be very careful about how you manage your persistent volumes, and then also you need to be very careful with how you manage the keys. In general, we have often taken the perspective historically that dealing with blockchain should not be significantly different from dealing with operational runtimes from a DevOps perspective or from a cluster management or cluster administration perspective. They should act as any other distributed system that you might be running. And there's really only one key difference in general that you need to take into account. The first big difference, and that big difference is how do you manage the keys? So if we compare a blockchain-based system to, actually while I'm talking, let me go back to the exciting demo of our CI system. So the difference between running a blockchain network in a cloud environment or an on-prem data center and, for example, running something like etcd or an Elastic Search cluster or any other sort of more traditional focused distributed system. The big difference is how do we deal with the identity of a particular runtime? In other words, how do we deal with the cryptographic keys that we are managing and having one-to-one mappings with a particular runtime? In more traditional fault-tolerant distributed systems that we run in cluster, we don't typically have to identify a particular node via a particular identity. However, with a blockchain system, pretty much every blockchain that I know of has a strong linkage between a particular public-private key pair and a particular runtime. That is how, at the network level, we identify a particular runtime as being this thing. And then this thing gets various permissions depending on the distributed ledger technology or framework that is running it. And so when we give it that particular permissions, we have those permissions, as far as I know, are always tied to a particular key pair that is then submitted to a runtime. And this is different from traditional, from earlier generations of fault-tolerant distributed systems, which you don't have a strong identity linkage between a runtime, so a particular node within an Elastic Search cluster or a particular node within an etcd cluster. Those things are not necessarily tied to a particular identity. And this is the big difference in running a blockchain network from an operator's perspective and running other distributed systems. So if we look at how we do it, this is a relatively simple bash script for those that know a little bit about Kubernetes. Does anybody have no idea what Kubernetes is? I probably should have started there. Okay, good. Okay, one person, great. Two. I didn't mean to call out people, so don't feel shy if you don't know what it is. Kubernetes is a cluster management framework that allows us to take a cluster of cloud-based nodes. We have, I think, 30 nodes currently, and we can manage those essentially as one Docker runtime. And underneath the hood, it deals with abstractions that allow us to manage at a cluster level volumes and runtimes. Cube conference, I think, is this week as well, and if I was at Cube conference, I would not be saying that, and maybe all of those people will burn me at the stake for that description, but that's how I think of what Kubernetes is. And so this bash script, essentially what it does is it removes our old state, and then it sets up a new state in config maps. And this is the piece here that does that job. It is a simple wrapper around Borough's configuration system. So within Borough, we have low-level tooling that allows you to define what your business network is. It does some similar things to how Composer allows you to set up your business network. I think they're called in Composer modality. Although I think Dan was in here. Are you here, Dan? Is that the right terminology? Business networks? Okay, yeah. So within Borough, we have two commands that we use. One is called spec, and the other is called configure. And spec, what that allows you to do is to say, in general, I want a network that has these types of accounts on it. And these types of accounts can be custom configured, or you can use the off-the-shelf abstractions that we use. And so you can say, for example, I'm going to have 7 developers on this chain. I'm going to have 5 validators on this chain, or I'm going to have 105 validators on this chain. And what the spec will do is it will outline for you a specific specification file that you can leverage to then, when you want to boot that network, use a different tool, or a different command, sorry, that we use, which is called configure. And what configure does is it says, okay, I have this specification for a network. Now I'm going to generate or use specific keys. And then when I generate or use specific keys, I'm going to map those to the specific specifications for the accounts that have been set up in the specification file. So if you see here this, just one second, line number 89 in this system, what it's doing is it is saying, given the specification, I want you to generate some keys and or reuse or map the public keys for things I have not been given keys I have been given in the specification file. And then finally what it does is it generates a specific Yamo file and it sends that to the Kubernetes system. It's API internally, and what that does is it sets up our keys and maps them to particular validating nodes. Now, this is the hardest part, in my opinion, of dealing with blockchains in the cloud, and it's the biggest difference from how you run other stateful distributed systems. So, what does this look like? Hold on, is that big enough to be read? I know you love my color screen. So for this network, I'm not worried about, for this network we use Kubernetes secrets to store the key pairs. For our production system, we use a different system, but for our demo environments, we use just Kubernetes secrets to manage the keys because they're relatively simple to inject into runtimes. And so what you're seeing here are the base 64 base 64 encoded keys that I just actually added into the system. So we save those as Kubernetes secrets, and then we also save a different sequence of keys. These bottom 4 fields here, node validators, no key validators 0 to 3. This is a 4-node network, a 4-validator node network, and those keys right there are different because in Borough we use two sets of keys. We use one as a signing key, and that is a ED22519 based elliptical curve. And that elliptical curve is not very good for connecting over a network. In fact, it's actually really bad at being able to do peer-to-peer connections. And so we use a slightly different key pair for peer-to-peer communications to be able to authenticate a particular node. We use the elliptical curve Diffie-Hellman key that is there. And so we map two sets of keys to each particular node that is running on the network. And so if I just pull up the configuration file for a particular node, yeah.
Are you concerned about size of those keys when you use secret?
Am I, sorry? The size in terms of data? Or, yeah. So the question was, am I concerned about the size of the keys? Typically, no, because elliptical curve key pairs are usually very, very short, particularly as compared to RSA keys. But in general, Kubernetes secrets are, I don't actually know what the maximum capacity is, but it's made to hold much bigger key pairs than elliptical curve typically are.
I remember right, it should be in
Yeah,
there.
so yeah, no, I don't know of any elliptical curve keys that would even come close to that. Yeah.
Where would you keep the key in production?
Not something I'm going to talk about here. How about that? We use a different system, so because that's our production system, I don't want to have too much leakage there.
Would you advise to use secret?
So, well, let me say it this way. I'm not in the security game, so I don't know if Dave is in the room or somebody else. Others would have be much better to talk to about that. I will say that Kubernetes secrets are used for really high-value API keys in production every single day. I know many systems that keep various, database logins and other things in Kubernetes secrets. So, how it might work for you would be a dependent thing. But Kubernetes secrets certainly works fine for managing the keys on demo environments, proof of concept environments, even pilot environments. I would be comfortable doing that. In production, I would be a little bit more careful. Just because, well, it would depend on the value that you're putting on any one particular key, but that's kind of a different architectural discussion. Yeah?
Who generates the keys for all departments?
So in Borough, we have an ability in spec files, we can say here is a public key for this particular identity or user on the chain. And so when you have, how we do it is we have developers that generate keys on their own laptops and then send in the public keys, and we put those in the spec file, and then we generate in cluster the validator keys in the system that I'm just showing you in our demo environments, because then we have less traffic around where those keys are. So we generate them in cluster in an ephemeral container, send them to the Kubernetes API, tear down that container. The CI system tears down that container, and so in theory, because there may be some lag in there, but for demo environments, it's safe enough for us. Yeah. Any other questions? So then when we boot a particular runtime, if you look at these lines here, what this is saying is to mount the secret that I uploaded that had the particular key pairs, that is mounted into a directory that the runtime knows is where the keys should be. So then the Borough runtime has access to the keys that I have given it. And for our demo environments, what we do is, just to make things a little bit more simple operationally, we add all of the keys into one particular secret, and then we mount that secret across all of the runtimes. So all the validator runtimes, they actually have access to all the validator keys. This isn't something that you would do in production. In production, you would do a one-to-one mapping, but depending on sort of how you set up your secret management system, if you used other systems or used Kubernetes secrets, you would isolate these a little bit more. But for a proof of concept environment, for a demo environment, for a pilot environment, I would say it would be fine. I would be comfortable running it like this because, again, what you're only showing here is the keys that one portion or one entity of this particular blockchain has access to. So this wouldn't be all the keys. This would just be all the keys within my cluster. And so we mount that into the runtime. And then the second thing that we have to do is we have to manage what are my identities. And I said earlier, there's two pieces from Borough's perspective. There's two pieces to its identity. There is its signing identity, and there is its peer-to-peer identity. And these are independent of one another. However, at the network level, within the validator's object within a Borough runtime, there's a mapping between the two. So how do we get it, the validator key? Well, I showed earlier how we inject a particular validator key with a number in. And with each of our nodes in the Helm charts, which I'm going to show in a minute, we then set up a very simple mapping that all this does is it copies the particular node key, and this is the peer-to-peer key. We copy it from the Kubernetes secrets into the place within Borough where Borough expects that key to be, and then we give it the correct permission so that it can deal with things. And then the final bit is how do there we go. And then the final bit is how do we give the particular node its signing identity. And within Borough, we have a flag to do this. It's called the validator address, and you can see there that we've given this system a particular validator address. And I'll show how we do that in the Helm charts here in a second. So we handle the population of all of those identities at two levels. In a network init job that I initially showed, which then inputs into the Helm charts, which actually deploy the runtimes. And so now, before I start talking about Helm a little bit, does anybody in the room not know what Helm is? Anybody willing to admit that they don't know what Helm is? Okay, Helm is it's how it markets itself is as a package management system for Kubernetes. And essentially what it is a templating system over Kubernetes configuration system. So at a core level, how Kubernetes works is that it is really a series of YAML or JSON files that allow you to say, I want the runtimes to look like this, And then under the hood, Kubernetes basically says, okay, I'm going to make the state of the world look like that. And so it's a declarative system that allows you to say declaratively, this is how I want the world to look. And then what Helm does is it takes those base YAML configuration files that declare to the Kubernetes API server how you want the world to look, and then it allows for a templating and management of a whole range of different systems. So if you want to manage services, which are essentially cluster-level ports, ingresses, runtimes, which come in a couple of flavors, all of that can be done as a package around a particular system that you want to send to into the Kubernetes platform. So what a Helm chart looks like is, like I said, it really looks like a series of YAML files. And these charts are the ones that are within the primary Helm repo for Borough are a bit old, so I'm showing our little bit more updated ones. And what we do here is we essentially have to understand where, which node am I using? And so what you'll see here at the top is are some abstractions around defining what node number this particular system is. And what Helm does is we have an ability to say, I want a 7 validator node network, or I want a 5 validator node network, or I want a 4, or however many validators you want to be running in cluster. And then the Helm chart will populate the runtimes, which this is a deployment runtime for those that are familiar with Kubernetes and how it has different runtime systems. And when this system is deployed, what it will do is it will loop through with that range query at the top. It's going to loop through the deployments until it has set up the number of deployments that you have defined for this particular network. And then what it will do is it will populate the node identification system in what's called an init container. So this is exactly what I showed earlier in terms of the deployed pod. This is how it looks in the templating system. And then this is how the validator addresses look. Now this is really, frankly, this is really ugly code. But it is about the best that we have been able to get to in terms of dealing with the keys. So essentially what we do is, if you see on line 85, before we do the Helm chart release, we tell the Helm chart what are the what are the addresses of the particular nodes, and we give it to that in an order. And that order then determines what key any one validator on the network uses. And then at the spec level, we have mapped that node to the ability to be a validator on the network. So these Helm charts are relatively easy to use. The way that Helm works in general is that it works on this idea of values files. And values files are essentially the parameters that you want for running this particular package, if you will. And so you can see here at the top we have the image, and then we have some chain configuration stuff. We have within the chart an ability to add extra seeds, which are nodes external to your cluster that you want to connect into. You set up the number of nodes, log level, other things, and then you have the validator addresses object, and that validator addresses object is what tells you the addresses, both the signing address, which we call just the address, and the peer-to-peer address, which we call the node address, and then some other normal runtime configuration, such as do you want to open external to the cluster, various ports. In Borough, we have a range of ports. We, of course, have the peer-to-peer port. We have a gRPC port. We have an info port, which serves over HTTP, very, very specific information about the Borough runtime. And then we have metrics, profiler, and a few other ports that we use. Now, once that system is up and operational, then what do we do? So if I go back to the CI system that I triggered at the beginning, what this did is it booted a cluster of Borough nodes, which are these lines here. So Terraform outputs for us what are the public key addresses. And then we run through a sequence of sending a quite sophisticated, well over, I would say well over 22,000 lines of Solidity code that was then deployed onto the system. And then we boot our application level runtimes on top of it. This is the system here that is booting that. And then when we push that together, within this namespace, all of these runtimes were booted, configured, and talked to one another in that sequence. So we have some UI containers here. We have an Oracle container here that does some Oracle stuff on this particular platform. Notifier runtime. We have the Borough configured nodes right here. And then we have the primary API containers here. We have a Postgres that we use for querying. Vent, if anybody is interested, Vent is a system that we built that allows you to take events that are emitted via Solidity code on a Borough chain and send those as configured objects into Postgres, which makes it significantly easier to query sophisticated information that you get from a blockchain environment. And then also we have our system Horde, which is a content addressable system that allows us to have content addressability over cloud buckets, local file systems, or IPFS. It also does pretty sophisticated encryption. And so then the next thing that we really need to look at is log management. So we use in system, one of the advantages of leveraging Kubernetes is that off the shelf we can pull an Elasticsearch and an Elk stack, and we run a really quite standard Elk stack for Elasticsearch, Logstash, and Kibana. And this Kibana here is showing the dashboard that we have set up for the runtimes, the Borough runtimes. And you can see here that these are just the logs. And in Borough, we have mostly everything is relatively easy for an Elasticsearch system to manage. All the logs are JSON formatted as long as you choose that option, and that makes it relatively quite easy. And then within Borough, we have inbuilt Prometheus system. And Prometheus is a cloud-based monitoring system. It's housed within the same project as Kubernetes. And this is Grafana. Grafana is just a front end for Prometheus. And so we have an ability to then monitor what are the PVCs, what's the mempool looking like, what are the transactions per blocks, blocks per minute, quantiles around the blocks, CPU usage, memory usage, and other sort of low-level Go primitives that we can then track from our monitoring system. Obviously, what blocks are we on as well. And so this is, with 5 minutes left, this is how we do monitoring and how I wanted to kind of wrap up here. I know this has been kind of a whirlwind, and if somebody isn't deep in cloud technology, this may have been a very boring talk, I realize, but which was why I had it be advanced. But in any event, what we have tried to do within our systems and within Borough in particular is to close the gap between how an operator or a cluster administrator would think about running a traditional distributed system, something like etcd or Elasticsearch or any other Zookeeper, any other system along those lines. And to make that as approachable as possible for running blockchains. And that's why we have inbuilt Prometheus metrics. That is why we deal with logs in the way that we do. That's why we have published our Helm charts and other things. And when you treat blockchains just as you would another stateful distributed system, with in my opinion, the single exception, which is around managing keys and then mapping keys to particular identities of a runtime, then it makes your life a whole lot easier, because then as a cluster administrator, because then you're not thinking of blockchains as some other thing, but rather are just integrated in. And an example of this is that when we submitted our Helm charts to the Helm repo, you know, the Helm repos have a CI system that manages, does this thing boot or not, essentially. And they can do that for a whole range of distributed systems. And we were the first blockchain to be submitted into them. And so I had to talk to the maintainers about the differences between running blockchains and others, and between us and then just after we started, somebody from Microsoft was working on getting Ethereum charts in there as well. And between the two of us, we were able to say, okay, within the CI system, we essentially need a way to manage keys, but outside that, the CI system should run off the bat. And so they gave us an ability to have essentially a testing YAML, and with a single testing YAML where we could set up keys, we were able to instantly run and pass all of the CI systems. So with that, I have about 5 minutes left, or maybe less. Yeah. Are there any questions? Yeah. Here. Oh, what CI system do we use? We use GitLab CI. For our open source stuff, for Borough and for Blackstone, we use Circle CI, and then for our own internal systems, we use GitLab and GitLab CI. Yeah.
So, how do you handle adding and removing nodes dynamically, considering you've pre-generated the validated keys initially and you're mapping them? So you have a predefined set of keys that you dynamically set to new nodes.
Mm-hmm.
Can you elaborate a bit?
Yeah. So this is another difference in how you deal with blockchains versus other systems, in that blockchains don't really horizontally scale, and you can't do it manually. You can't do it automatically. So if we just scale up the number of runtimes within the system, that won't actually work. So we do it manually. We would generate a new key, a new 2 sets of keys. We would then upload those into the particular place, depending if it was a demo environment or it was, well, we only really do this in production because in our demo environments, we would just rebuild the whole thing because it takes about 10 minutes. And then, so you would add new keys, and then you would boot the runtimes with those key pairs. So it's a little bit more manual how you horizontally scale blockchains.
You don't have Helm charts for new node. You just have Helm charts for the whole network deployment.
Right, for the initial network deployment. It wouldn't be too hard to add. I mean, you could run a Helm chart. The charts are pretty flexible. They could be ran with a different release that would then do your new keys. And because of Helm manages its state pretty well. I think actually if you just added a new chart and reran on the same release, it may or may not work, but we've never actually tested doing it that way. So, yeah.
On the same node, if one of the existing node comes down, also this gets, because as if it's an addition of nodes like this. Is that correct?
So is your question, how do we deal with node failover? Yeah, okay, that's something that I missed. So we struggled with this for a little while, how we deal with this. And the key thing that you really need to know is if the runtime exits, so if the runtime exits, Kubernetes knows that it exited and it'll boot. So that part is fine. The harder part for us to deal with is the runtime's still going, but for whatever reason, this runtime has become disconnected from the network, and this runtime isn't making blocks. And so within the info port that I talked about, we actually build a system where you can query the runtime to say, have you made blocks within this last minute, 5 minutes, 10 minutes is configurable. You can say, have you made blocks within this time X? And so with our liveness and readiness probes, which is how Kubernetes tells that a runtime is still doing what it should be doing, we use this endpoint and we essentially ask the Borough runtime, have you made blocks within the last three minutes, I think is how we currently have it configured. And the Borough node, if it has not made blocks within those minutes, will then give a 400. I think it's a 4 or 500, but anyway, it'll give an error HTTP code, which will then signal to Kubernetes to fail over that particular node, which almost always then reconnects the node, and then it'll carry on. Because obviously the state is handled in volume, so the state doesn't go away when you fail over the runtime.
So the old secrets and everything will just carry.
Yeah. It'll just reboot with the secrets mounted, and the old blocks and data are in a persistent volume, so it'll just connect that and it'll say carry on. So that's how we deal with node failover. But that was an interesting thing that we actually had to build a custom system to do, because when the runtime was working, if it was on, then that wasn't really the biggest concern. Anybody else? I think I'm over time anyway, so sorry to whoever's next. Yeah.
So that question was regarding the physical nodes.
Yeah. Sure.
The question is regarding multiple pods for each peer node.
Okay.
Behind a Kubernetes proxy object.
Okay.
So, how many nodes, how many pods you have in a production environment? 3, 5. So, basically, in Kubernetes,
Mm-hmm.
you have a proxy object
Mm-hmm.
okay, acting as a load balancer.
Mm-hmm.
You have multiple instances of the same Docker image.
Yep.
Running, right?
Yep.
So, those are, if one of them fails, crashes,
Mm-hmm.
Kubernetes will bring up another instance.
Mm-hmm. Yep.
So, but each of the peer nodes, they are storing the blockchain on the underlying physical disk.
Mm-hmm.
How do you handle that in a production environment
Mm-hmm.
when you have all of them should have the same underlying blockchain
Are you talking about the data that is saved on disk from the blocks and state? Yeah, okay. So how we deal with that is Kubernetes abstraction called persistent volumes. So we save everything in persistent volumes, which maps to the persistent volumes within the cloud providers. And so those persistent volumes can get moved around and mounted on physical disks, actual machines, and then exposed into Docker runtimes. Kubernetes handles that really elegantly. It's one of the primary things that Kubernetes handles. Once you declare a persistent volume claim, then all the data is saved onto that, and then even if the node moves around on physical machines, Kubernetes handles the mounting of that volume and then the booting of the runtime over it. Thank you very much. We'll be here all week, so ask us any more questions.